Hello and welcome. Today I would like to discuss the changes in the 2020 edition of the Industrial Piping Code in EN 13480-3, and I want to have a special look on the impact it has on pipe stress analysis with ROHR2. To give you an overview, we'll start with an introduction, discuss the stress intensification factors, how the axial forces are taken into account in the stress equations, how the alternative stress intensification factor for in-plane and out-plane from table H3 are integrated in the alternate equations, how the corrosion is taken into account, and we finish with a conclusion. In 2015, the working group working on the EN 13480-3 launched an update of the stress analysis calculation chapter 12. The goal was a coherent treatment of the corrosion between the internal pressure analysis and the flexibility analysis. The specification of the equations to use the stress indices from H3 in-plane and out-plane factors were taken into account. The actual loading were also included in the stress equations. This was especially required for the buried pipes in view of the part 6 of the same norm. Also some inconsistencies for the stress indices of T's were removed, and the increased bend thickness due to EN 10253 was also taken into account. If we look a little bit at the history, in 2015 the working group launched the update of the stress calculation of chapter 12, and in 2016 a first version of the draft amendment PRA2 was created. And ROHR2 implemented this draft, which could be activated at the time by modifying the registry entry. In 2018, ROHR2 implemented the parallel calculation of the code according to version to edition 2017, and so this was a code that was correct at the time, and also the PRA2 version in parallel to avoid errors with actual forces. This was applied by default unless the user choose to only do the 2017 version. Now, in the end of 2020, the EN 13480A2 was finally published, and ROHR2 implements this amendment A2 as default and leaves the old version as an option, and this is starting from ROHR2 version 33.1. So, as a small summary, most users have already been checking their system against the criteria of PRA2 or now A2 since 2018, so 2 years before it actually became a code. So let's have a look at the details. Stress intensification factors for T's for the flexibility calculation in chapter 12 are given in Annex H, and when the stresses are verified for a T, 3 different sections are verified. First of all, the run with a sectional modulus of the run and the bending moment of the run, and for the branch 2 sections are verified: the branch away from the run, just the straight pipe, and also the run wall thickness around the branch using the stress intensification factor. And this is realized by using the thin wall formula for the sectional modulus with a virtual wall thickness EX. And this is specified in the Annex H in the table H1 with the column sectional modulus, which is different for the header and for the nozzle. And for the nozzle there is this different wall thickness EX, once for the branch and once for the run around the branch. To understand the problem with this current approach, we have to look at the section of the run around the branch, and currently it was evaluated based on the average diameter of the branch and the wall thickness of the run. Now if we take the situation where we keep the outer diameter of the branch constant and increase the wall thickness of the branch so that it goes thicker on the inside, the average diameter will decrease, and in that case the sectional modulus for the section that we evaluate will also decrease. So if we look at the stresses, while we increase the wall thickness here of the branch, this is shown down here, you can see that the stresses will first reduce, that is when the section of the branch is the weakest section, and then suddenly it starts to increase again, and that's when the run is the critical section. And this is of course not realistic, and this behavior cannot be reproduced by finite element analysis. Now, how was this solved in the new approach? First of all, the column with the sectional modulus was removed and was replaced by a footnote, and in this footnote the sectional modulus now is calculated as the outer diameter of the branch pipe. So this is corrected by using the outer diameter, and this translates to the stresses will decrease with an increase of wall thickness, and once the branch is no longer the critical section, it's the run, then the stresses remain the same if you increase the wall thickness inside of the branch. That has no effect on the stresses, and that is more realistic. Now, what's the impact on a real pipe stress calculation? First of all, if the branch itself is a critical section, so this would be for thin branches, then there is no impact. If the run is the critical section and the thickness of the branch is very high, so here's an extreme value with a DN18 with 27 mm of wall thickness, and then the 2017 version, in this case here example of an S4 equation, was as 92% stress utilization, and this goes down all the way to 44% here. Let's have a look at the graphical user interface of ROHR2. In the load case definition, I have specified 3 different stress equations. The first one is the one with the 2017 version alone. This is done by specifying calculation according to version 2017, and also specifying do not consider the PRI2 amendments. In the next line, I've made a mixture of PRI2 and 2017, so I checked 2017, but I say please keep PRI2 active. This was the standard setting for ROHR2 version 33, so unless you uncheck this, you got the worst case of these 2 combinations. And now in the new version 33.1, the standard would be to calculate according to the 2020 version, which is now released, and to no longer consider the older versions. So if I look at the results, and I want to have a look at the S4 equation here, the thermal stresses, I can see that the stresses here in the T, in the branch of the gas storage tank, the stresses are quite high. They have been optimized so they're just in the acceptable level. And in this case, the branches are extremely high wall thickness branches, because the storage tanks are limited due to internal pressure, and all the reinforcement is done in the branch connection. So that's the DN80 with 27.6 mm of wall thickness. And if I check the stresses now with the correction of the stress intensification factor of the new code, you can see that the stress utilization goes significantly down. It almost goes down by half. And if I look at the combined version with the old and the new code, of course you can see that the old 2017 version was dominating, and you would get the results from this old code. The next subject I want to discuss are the axial forces in the calculation for the flexibility analysis in chapter 12. And here the problem is that the current or the previous version did only include the internal pressure term in the actual stress analysis, and this is not sufficient in case of significant actual stresses, such as the ones that could happen in buried pipes, or in actual restraint pipes, or in pipes that are used for supporting structures. Now, the solution that was adopted is similar as in ASME B31.3. We now specify the primary stresses, defining the total axial force and the contribution from the bending moments, and the total axial force now is takes the contribution from the pressure, but also from the sustained axial loads QXS. And because the pressure can happen or not, we have to take the maximum of either with or without the internal pressure. Now, for the occasional equation sigma 2, the situation is very similar. We define a total axial force and the contribution from the bending moments, and now for the total axial force we have to do all the combinations that may arise during the different load situations, and therefore we have to decide whether we are talking about reversing loads which could have positive or negative signs, or non-reversing loads which have a determined sign. And so all the combinations with the correct signs are added up, and the maximum is taken here. Now, what's the impact on the stress calculation? For normal industrial piping, the actual forces other than from internal pressure are negligible, except for buried pipes, double jacket pipes, and pipes element used for supports, or if someone has done a modeling error and has put some actual stops in a straight line. So if we take the example from our gas storage tank here again, and we look at the straight pipe in the buried part of it, we can see that the stresses are reduced for the S1 equation from 27% in the 2017 version to around 23% in the 2020 version, and this is due to the actual forces which are now based on the internal diameter, which is slightly less conservative than the old equation with the actual stresses due to pressure. Now if we look at an example with a buried pipe, we can see that the stresses for here, thermal stresses from S4 equation from the 2017 version increase from 83% to 128% in the 2020 version, and this is because the old stress code was not considering the actual forces due to restrained thermal expansion, and this of course is not correct, and the old code could not be used to verify buried pipes with long straight segments. Here's another interesting example from a pipe used as a supporting structure. So here is a steam drum that is supported on some lines, and you just a comparison of different situations. One it's hanging down and once it's standing up, and we can see that in the old code the stress utilization was 79%, was the same if it was hanging up or pushing down, because we have at the same time a higher internal pressure and an actual force, which was not taken into account in the previous version. Now with the new version, if they end up increasing the actual stresses, so if it's hanging down, we have a higher stress utilization of 89%, whereas in the opposite direction there is no impact. Here is another extract from a normal above ground piping system, and we're looking at the S4 equation here, and we can see that there in a normal piping system there is no difference between the old and the new code, and most piping systems above ground don't have any significant actual forces, so that's normal. But if we look at the situation with the modeling error, so here for example someone has forgotten two actual stops on the straight line, and now we can see that there is a significant difference between the old version and the new version, and the new version will directly show the stresses due to actual forces, and they will directly show up in the stress equation, and not only if you look at the support loads, which of course here are huge in this example. So this error could previously only be detected by looking at the support loads, and now it shows directly up in the stress equations. Now in the stress equations you can find the reference to the stress indices EI, and these are given in the table H, annex H, in the column stress intensification factor for the different components. But if you look at the table H3 in appendix H3 for the in-plane and out-plane stress intensification factors, you have no specification how to use the II and IO values in the stress equations. There is currently no alternative stress equations specified. Even worse, there is just a sentence saying you can replace 0.75i by II and IO, which basically removes the 0.75 from the primary stress equations. Now how was this solved? We now introduced the alternative equations, and in these alternative equations the way how to use the in-plane and out-plane factors are used as described, and now you can see we correctly use this 0.75 times I in the primary load equations for II and IO, and it's also specified how to combine the mending contribution with the actual loads and the torsional moments. And of course this is more complicated than just replacing I by II and IO. Things get even more complicated for the stress range, because now we have to calculate a stress range based on in-plane and out-plane moments, and we also have the fact that the in-plane and out-plane stress intensification factors also are load case dependent because of the pressure stiffening of the bends. Therefore the new stress equation needs to correctly specify that we have to build the biggest difference between two moment situations, including different SIFs. So now this has to be a stress range and no longer just a moment range. As this approach is very similar as in ASME B31.3, We also included the fact that the axial forces now can have a stress intensification factor, which is given as 1 until new factors are specified in the norm. Now, what is the impact on the stress analysis? For ROHR2 users, there's actually no impact because the alternative equations are already implemented in this way in ROHR2. The advantage is now that you have a calculation method that is nicely documented in the stress code as well. Let's also have a look at the corrosion allowance. The problem is here that in the internal pressure design calculation, corrosion and erosion needs to be taken into account, but chapter 12 is not very clear about it. The original terming was almost contradictory, because it says on the one side that the stresses should be determined on nominal thickness, so without corrosion and without manufacturing tolerances, and then the next line says the wall thickness reduction due to manufacturing tolerances does not need to be taken into account. So these two could be interpreted in a very different way. How was it done in other stress codes? Now, if you look at the old FDBR code, the stiffness was calculated based on nominal thickness, the sieves were calculated using nominal thickness, and the calculation of stresses were calculated using the corroded thickness. The Codeti was using the same approach, but it also used corroded thickness for the stress intensification factor in some version, which is now been removed in the latest edition. And ASME 1313, the calculation of the stiffness is used on nominal thickness, and the sieve is also calculated on nominal thickness, and the primary stresses are based on corroded thickness and the secondary stresses on nominal thickness. And this is the latest approach from B313 was also taken over for the 13480. This was done in such a way that the corroded thickness was defined, and this corroded thickness is used to calculate the corroded sectional modulus, and this corroded sectional modulus is used for the calculation of the primary stress equations, whereas the non-corroded sectional modulus based on nominal pipe is still used for the secondary stress equations. So you can see the difference here between those two. And in ROHR2, what would be the impact? First of all, the corrosion is specified here in ROHR2, and this is still the case, so there is now a modification in ROHR2, and now you can choose if you want to consider the corrosion for the primary part, for the secondary part, and for the internal pressure part. So for ROHR2 there is no change. Now in this video I'm not going to discuss the changes to the how the bend thickness is taken into account. I probably need a separate video for this one. So let's come to the conclusion. The new EN 13480 industrial piping in edition 2020 has changed the stress analysis. The stress intensification factors for the T are now more realistic, especially for thick wall thickness branches. The axial forces are now taken into account, and most ROHR2 users have done this check already since the year 2018. The alternative equations are now explicitly written in the stress code, and ROHR2 users have also been using these for some years now. The corrosion was clarified. This is also the standard in ROHR2 for some time. So most of the changes in the new standard just confirm the way the stress analysis was already done in ROHR2, and very little is expected as a change when applying the new version. Thanks for listening, and hope you tune in next time.